The final talk of this morning session is by Dr. Maxime Maurice from Rice University. He just arrived there 2 weeks ago. We call it freshly baked PhD, right? You're doing your postdoc there now, right?
Yes.
Yeah, okay.
First of all, thank you very much for inviting me and giving me the opportunity to present this work I've been doing during my PhD. Which has to do with the thermal evolution and the crystallization of the lunar magma ocean. I would like to acknowledge also people I've been working with in Berlin during my PhD. First of all, Nicolas Tosi, who was my PhD advisor, Sabrina Schwinger, and also Doris Boyer, who is the head of the department of physics of the interior of planets at TLR, and which you heard, I think, in the previous seminar. And I also acknowledge the late accretion project, which is involving several universities across Germany and which helped me significantly during this PhD. So I guess this talk will start a sort of a new session, more science-oriented than the 2 previous talks, and which will probably follow pretty much the same this afternoon. So it will be organized a bit more as a scientific talk, which means I will first give you a brief introduction of the context of the magma ocean, the whole idea and concept of the magma ocean on the moon, and bring up the whole problem we are trying to address, and present the model we've been developing and the results and what it means for the broader outlook. And to begin with, I will give you a quick introduction to the formation of the moon. I will be brief on that since you will have a talk on the topic this afternoon, much better than what I can do, because that's really not not really my field. But I will try to give you an insight, especially in the light of how it relates to the formation of the magma ocean on the moon. So pretty much today it's firmly established that the moon was created in the aftermath of a giant impact between the proto-Earth and a stranding planetary embryo. As you can see in this video, where you have the proto-Earth here and the impacting embryo. And this is for the so-called canonical model of giant impact. There are a few of those models, but in a broad sense, you see that it involves several impacts between those 2 bodies and creation of a disk of debris around the young Earth. So this is all going pretty fast. This video is a matter of some hours, I guess, or maybe some days. And the color code indicates entropy, which roughly you can assimilate to temperature here, where the lighter parts would be hotter. And you can't really see it on this simulation, but actually it would most likely involve also liberation or massive liberation of gases, in the sense that what you can see on this video is only condensed material. But if you were to also see what is not condensed, still in the form of gas, you would probably see something more like that on a similar length scale. And this is an artist's view for what is called the Synestheia, which is a speculative object of what the Earth-Moon system just after the giant impact could resemble. And as I said, it's highly speculative, and actually the thermal state of the Earth after this giant impact is highly under constraint. But in this model, you have to imagine that it's all wrapped up in a cloud of burning gas. It's something like several thousands of degrees. So it's really hot. And it's been shown that this cloud of burning gas can even go as far as encompassing the initial orbit of the forming moon. So if the initial thermal state of the moon, of the Earth is poorly constrained, and the initial thermal state of the moon is even less constrained, one thing is pretty much sure: it was really hot back then. However, as you can see, that's not sufficient to put quantitative constraint on the thermal state of the early lunar mantle, in particular to say whether or not it had a magma ocean or how deep it was. But at this point, would back what was said in the first talk by Jim about how important all the material which was brought back from the Apollo and Lunar mission has proved when it comes to lunar science, because actually the first strong evidence, the whole idea of a lunar magma ocean really was born in the 70s when those samples were analyzed, those lunar samples were analyzed, and geologists figured out that there was largely composed of anorthosite, which is a form of plagioclase. And the best explanation, the more realistic scenario they could come up with for this mineral to be so significant on the surface of the moon was that it must have crystallized out of a deep ocean of magma, settle at the surface because it was lighter than the surrounding melt, until forming this thick crust. And it's not like just a veneer at the surface. Now we have evidence from Grail measurement that the anorthosite crust must be something like 30 or 40 kilometers in thickness, which is, by the way, also providing a lower bound for the models of the volume of the magma ocean, because you have to crystallize enough of this magma ocean to be able to produce this volume of the crust. So yeah, as you can see, most of our evidences for the existence of an early magma ocean come from the analysis of the lunar samples. Now that we are pretty much convinced that there was an early lunar magma ocean, I'd like to say a few words about why it is so important to be able to properly constrain its evolution in terms of chronology and in terms of what happened during this crystallization. First of all, also in the first talk, it was talked about the mare, which represents the main form of volcanism on the moon, which extends over a very long period of the lunar history. On this picture, you have a time series for the eruption of at the surface of the moon of these so-called mare basalts, because they compose the mares, which are these dark spots that can be seen on the moon. And it's been observed that some of these mare basalt samples that we have are enriched in titanium. And it's been a question since we discovered that. And in particular, we saw the pictures of these green and yellow glasses, and some of them, I don't remember which ones, but some of them are the highest, show the highest content in titanium, as much as 17%. And it's always remain problematic to understand where this whole titanium comes from. Well, not so much where it comes from, but how a high titanium reservoir entered the composition of these mare basalts. And that is most likely how the magma ocean crystallized, and how long it took to crystallize is most likely had a strong influence on the possibility to mix up a high titanium reservoir. Another influence it might have, and I find personally that's really fascinating, is that the evolution of the Earth-Moon orbital system can be related, can be coupled with the evolution of the internal thermal state of both the Earth and the Moon, in particular of the Moon, meaning that according to the models of moon formation, the Moon formed much closer to the Earth than it is today, which means that the orbital parameters of the Earth-Moon system have evolved through time. And I mean, not only the semi-major axis, but also the eccentricity, the obliquity. And all of these can be related to the internal thermal state of both bodies through the effects that they have when they exert tide. So you can have tidal dissipation of orbital energy, which would contribute to heat up the bodies, and which means that if you dissipate more efficiently in the Moon, you will have a significant damping on the orbital parameters, much more than if you can't dissipate, if it's too stiff and you can't dissipate enough. And the presence of a magmotion on the Moon plays a crucial role here. Then, of course, there's a strong influence on the distribution of trace elements, which are partitioned in the magma ocean. And that means that it has a strong influence also on the isotopic system that I used to evaluate the age of the lunar samples. So if you want to have a robust estimate of the age via measurement of isotopic ratio, you have to understand the underlying physical process that led to the fractionation of these isotopes. And finally, this might be a bit more anecdotal, but it's still quite interesting. It might also have an influence on the relaxation of craters, in the sense that if you have very early craters which were formed on the crust of the Moon while the magma ocean was still present below it, then those craters would most likely have relaxed by then because of the physical constraints that were different. And this means that you have to, that's something you want to take into consideration when performing crater counting age measurements. Okay, so now that we are convinced that it's very important to understand how the magma ocean on the Moon evolved, I will review a few constraints that we have on this chronology. So here I put a timeline actually graded with Earth eons. So going from the formation of the Earth, pretty much the formation of the solar system to today. And actually a funny fact is that most of you guys are a bit ahead of me on this timeline since you are already the 14th of January, while I'm still on the 13th, but we don't have the resolution to see that. Now I'd like to make a close-up on the first 300 million years from the formation of this solar system. And here on this timeline, on this close-up, you see a few points which correspond to age estimates of samples of the lunar crust. And the horizontal lines are the error bars. So this doesn't necessarily mean that the crust was still forming as late as 4.29 billion years ago, because these ages might have been reset by resetting of the isotopic system, or it might also be just that they are not as robust enough to be significant, because often one requires at least that this age be concordant, be among two different isotope systems. But still, it suggests that the crust were at least undergoing strong transformation at this time. And actually, you have this circled M, which corresponds to the age estimate of the samples that you have seen earlier in my talk, which is the ferron anorthosite 60025, and which we think provide a very reliable age estimate for the crust, as it is concordant among various systems. And now here I would put another anchor point here, which is not a crustal sample, but which is what has already been mentioned in Jim's talk, creep samples. Creep meaning that it's rich in potassium, rare earth elements, and phosphorus. And it is thought to be representative of the very last drag of Magmotion to have crystallized, because it's so rich in very incompatible elements. And we think so that it really pinpoints the end of the Magmotion crystallization. And this is an age that was obtained by Emmy Gaffner and Lasborg. And you can see that it corresponds roughly to, here is the exact date, 4.369. It covers about this point. So we think we have the end of the crystallization of the Magmotion, but the beginning, which must correspond to the formation of the moon, is still an open question. So now I would like to present a few of the typical physical processes that you expect to take place in the magma ocean. So I will start with the general picture of the magma oceans. And you have, when you're thinking about magma ocean, you have to picture something really liquid undergoing turbulent convection, as a result of which you have an adiabatic distribution throughout the magma ocean because it's so well mixed. And you want to compare that to the solidification temperature of the material. Whenever you're below the solidification temperature, you have a solid-like behavior, at least on a dynamical point of view, whereas when you're above this temperature, you are liquid. It turns out, as you can see on this diagram, that the solidification temperature has a stronger gradient with depth, or radius, if you will, than the adiabat. As a result of what, those two curves first crossed at depth, and upon cooling of the magma ocean, that you see materials here, which corresponds to a leftward drag of the adiabat, you see that the crossing point of those two lines, which corresponds to the bottom of the magma ocean, is lift up through time. This is what we call the bottom-up crystallization of the magma ocean, and that's a common feature of magma ocean crystallization on most bodies which are big enough to have this strong effect of pressure on the solidification temperature. So now I'd like to jump on the more specific case of the lunar magma ocean. And what makes it so specific is, as has already been highlighted, at some point you form a plagioclase crust. So actually the beginning, before you start forming the plagioclase crust, which corresponds, according to the newest models, of the crystallization of about 80% of the magma ocean. So during the crystallization of this first 80%, you are cooling by radiative cooling at the surface, which is very, very efficient, which means that the crystallization of the first 80% of the magma ocean happen so fast that on a point of view of the time series, it's almost negligible. So then you start forming plagioclase crystals represented here, which accumulate at the surface and form an insulating flotation lid, which tremendously slow down the heat flux at the surface. And it's a decrease of about 8 orders of magnitude. So that's really a fantastic slowdown of the crystallization. As a result of which, the 20 last % of the magma ocean volume take much longer to crystallize than the first 80%. And most studies actually only focus on the crystallization of these last 20%. Here I review briefly two of the most important and most influential models for the Magmotion crystallization, for the lunar Magmotion crystallization. The first one, which was really set an important stone was from Solomon and Longi, 1977, where they simulated the crystallization of a fairly shallow magma ocean. I think the initial depth was between 200 and 400 kilometers. So in this case, you can see the evolution of the time series of the bottom of the crust here and of the magma ocean. So you see it starts a bit more than 300 kilometers. They considered, so as I said, a fairly shallow magma ocean. They considered also that the crust started forming quite early, after only 50% of the magma ocean crystallized, because back then they didn't have the most modern crystallization models that we have now. They also consider that the final crust, plagioclase crust, was quite a bit more, a bit thicker than what we expect now. But similarly, they didn't have the newest data from Grail and everything. So their model ended up predicting magma ocean crystallization in something like 200 million years. But yeah, with all the shortage that are due to the fact that they didn't have as many information as we do now. Then a bit further in time, another important and influential model was that of Elkin Stanton and collaborator in 2011, where they focused on the crystallization of the last 20% of the magma ocean when the crust started to grow. And here is a result of their simulation as expressed in the time series of the temperature of the magma ocean. So whenever the lowest temperature is reached is the closure of the magma ocean. And they show the results for different depth of the magma ocean when the crust started to form. So between 50 kilometers up to 250. In this model, they counted for the growth of the crust until I think something like 40 kilometers, which is in good agreement with what we think. And you can see that they came up with a maximum estimate of 35 million years, which is significantly shorter than what was predicted by Solomon and Longi. However, there are a few caveats in this model. The first of them being that the most important effects in this model, which is the cooling via convection in the crust, was parameterized by the thermal conductivity in the crust of 4 watt per meter per Kelvin, or slightly less, but close to that. And it turned out that anorthosite actually is one of the minerals with the lowest thermal conductivity. So this overestimate of the thermal conductivity in the crust led to an overestimate of the efficiency of cooling, and in turn of an underestimation of the lifetime of the magma ocean. Also, they neglected some other potential heat sources like heat production within the magma ocean. So in order to address these different caveats, we decided to implement our own thermal evolution model for the moon, being as exhaustive as possible. And first, we relied on a high resolution crystallization model for the magma ocean, which was developed by Sabrina Schwinger from the German Aerospace Center. And essentially what Sabrina did is that she used 2 different codes, which are in a sense Gibbs free energy minimizer, which are codes in which you give an initial composition in terms of major elements, as well as temperature and pressure conditions and other conditions. And from that, you can compute how much material crystallizes and what are the crystallizing phases. So what she came up with, first of all, is this crystallization sequence, where you can see here the evolution of the crystallization of the magma ocean in terms of % of volume solidified, and you can see the fraction of each mineral crystallized. So you can see that after 80%, we'll start crystallizing plagioclase, which will form the crust. So we are in agreement with the newest models. And this model has been done for an initially 1,000 kilometer thick magma ocean. And it was assumed that all these minerals which crystallize, they settle efficiently at the bottom, keeping a 5% trapped melt, all except, of course, plagioclase, which settles at the surface and form the crust. She also computed the fractionation of heat-producing elements. So heat-producing elements are incompatible, which means that they preferentially remain within the liquid. And actually here, the assumption was that they only stay in the liquid, which means that they only enter the solid part of the mantle, which we call the cumulates, through this 5% trapped melt. And finally, the plagioclase produced here corresponds to a final crust thickness of 42 kilometers, which is also in good agreement with the other models. What we are more interested in for the thermal evolution model is actually the solidification temperature, which corresponds to the crystallization of this magma ocean, and which is represented here as a function of depth. So the bottom of the magma ocean is here. Well, that's an artifact of the plot. The king should be actually here because we considered an initially 1,000 kilometer magma ocean. And as it crystallizes, as it cools, actually it crystallizes. And the temperature retained by the solidified part, which we call the cumulates, follow this line. And on the lower mantle, which was never molten, we assume an accretion-like temperature profile. And we also have the profile of the heat-producing element, which correspond to which are trapped in the interstitial liquid, and which follow a usual fractionation profile, where you see that it becomes more and more enriched because it becomes more and more enriched in the magma ocean, and in turns in the late crystalline cumulates. And finally, you have the content in the crust. So this gives us the initial condition for our thermal evolution model, which and we feed it with it. And here is what this model looked like. So as I said, we wanted to be as exhaustive as possible. So contrarily to previous models, which were mostly focusing on the magma ocean itself and the flotation crust, we decided to simulate the whole interior of the early moon, so that our model consists in 4 thermally coupled reservoirs. First, the core, which we consider isothermal, and which is exchanging heat with the mantle, heat-up cumulates by conduction at the interface. Then the mantle or the cumulates, which in the first time we consider conductive. So we solve the equation for heat conduction in a spherically symmetrical geometry. On top of that, there is the evolving magma ocean, which is also heated by the cumulates by conduction, and which is also heated within through the heat producing elements. And still on top of the magma ocean, we have the growing flotation crust, on which we also solve the equation for heat conduction. As I said, we consider internal heating, not only in the magma ocean actually, but also on the cumulates and flotation crust. And we solve all that in a time-dependent geometry, as can be seen by this time dependence, which corresponds to the fact that upon cooling, the magma ocean crystallizes and it shrinks, and the flotation crust grows as well as the cumulates. So our initial condition is what you have seen in the previous slide. So we start when the flotation crust is only 5 kilometers thick, which is just the beginning of the growth of the flotation crust. So after about 80% of the magma ocean crystallized, corresponding to a bit more than 100 kilometer thick magma ocean. And we assume that initially the cumulates follow the solidification temperature. And what it looks like is what you're going to see now in this video, where you see once again the initial state, and here is a close-up. So you see the flotation crust in gray, the magma ocean in yellow, and the cumulates in white. I didn't represent the core because it's not so interesting. And what you see when I start the video is that upon cooling, you see that the flotation crust grows, the magma ocean shrinks, and the temperature accumulates is slightly altered by diffusion. So you see that it's not exactly sticking to the initial solidification temperature, but not that much. And like you also notice the strong decrease in temperature towards the end in the solidification temperature. So for this case, the thermal conductivity in the crust, which is our main parameter, was 2 watt per meter per Kelvin, which is only 1/2 of what was considered in previous studies. And you see that we already reached a crystallization duration of 126 milliyear, which is significantly longer. So this is due not only to our choice of a lower thermal conductivity, but also to the other effects that we consider. And here is, for the same simulation, a time series of the heat budget of the magma ocean. So you have in blue the cooling flux, so the diffusion through the crust, which is lower than in previous models because we choose a lower thermal conductivity. But you also have the heating flux, which were not considered in previous studies, which are the internal heating by the heat producing element, which are partitioned in the magma ocean, as well as the conductive heating by the cumulates. And you see that this conductive heating is increasing towards the end due to the strong temperature gradient in the solidification temperature that I had you noticed before. So we led a small parameter study investigating various values of the thermal conductivity in the crust. And you see the results here in terms of the time series of the bottom of the magma ocean, the lower lines, and the bottom of the crust. So closure of the magma ocean corresponds to the intercept between those two curves. And you see that for the values which was previously considered, we reached crystallization in a bit less than 50 milliyear, which is a bit more than was previously thought, but that's also due to our difference crystallization model. While for our fiducial value, which is 2 watt per meter per Kelvin, which we think is the most realistic, we, as you've seen, we are already beyond 100 billion years. So you see that adopting a more exhaustive model as well as more realistic value of the thermal conductivity in the crust significantly prolongs the lifetime of the magma ocean. But at this point, we realized that, hey, this is actually taking so much time for the magma ocean that what we investigated in an earlier study might prove relevant. And in this earlier study, we actually showed that in some cases when the magma ocean was long-lived, you could have onset of thermal convection in the solid cumulates. So onset of a solid state convection regime in the cumulates. And in this study, we were mostly interested in mass and mostly interested in the composition of the cumulates, but still it's relevant. And here I'd like to draw your attention on this profile where you see the solidification temperature and the temperature in the cumulates in red. And you see for this case that in this case, the magma ocean solidification lasted only 1 million year. You can see here the bottom of the magma ocean evolving from this time to this time. And you see that at this point, we already saw that convection was occurring and causing this mixing in the solid parts, and which translates in this modification of the temperature profile from the initial solidification temperature. And this, so you see that here we're dealing with the timescale which is even much shorter than what we expect for the lunar magmotion. So we were, yeah, that was almost mandatory that for thermal convection to kick in before the end of the lunar magmotion solidification. And if you have convection in these hot cumulates, much likely you would expect to have secondary melting due to pressure release melting in the rising plume in this convecting mantle. And this secondary melting would then feed up the magma ocean and could help heating it up. So it's like as if you would have volcanism, which would spill its hot lava within the magma ocean. And this mechanism that we call heat piping is what we investigated in a second time by modifying our model. And this time, instead of considering that the accumulates were undergoing simple heat conduction, we simulated thermal convection within these accumulates. So we took just the same model, but instead of solving the equation for heat conduction, we used our convection code Gaia to simulate convection in a 3D full sphere shell representing the lunar growing mantle. And then we introduced a new parameter, which is the viscosity of these cumulates, which is pretty much how stiff the mantle is, and which is governing the intensity of convection. And also to have a good account on heat piping, the heat piping flux. So you can see here now on this part, this is a symbol for the convection, and this is the partial melting induced by the convection, and which is feeding a new term in the flux, which is heat piping. In order to have a good account on a good quantification of the heat piping, we parameterize the formation of melt due to pressure release melting. So we consider that whenever the rise of a plume caused the local temperature to exceed the solidus, which is this black dashed line, then we would produce enough melt to buffer the temperature via release, via consumption of latent heat, and that all the melt which was produced goes into the magma ocean, and that gives you how much heat you put in the magma ocean. And here is how it looks like. So now it's even a bit more visual since we have 3D convection simulation. That's the exciting part. So you can see here on the upper left, the lunar mantle, so the core, the lunar mantle, where you have a color mapping for the residual temperature. So you will see it when convection starts. You have the magma ocean, and on top of it, you have the crust. On the right, you have just a convective planform with the blue downwelling and red upwelling that you will also see when the video starts. And on the bottom panel, you have the time series of the heat budget of the magma ocean, where still in blue, you have the cooling through the crust. And this time in yellow, you have the sum of all the terms. So what was already included, the conductive cooling from the cumulates, the internal heating of the magma ocean, but also this time the heat piping flux. And now you will also see here on this panel that whenever melting is produced that feeds heat piping, it will be circled in black. So now I start the video and you see that convection kicks in, immediately resulting in melting, which is feeding the heat piping flux, and which corresponds to this big surge in the heating flux for the magma ocean. And you see that all the melt which is produced here in the melting plumes and which is feeding the heat piping in the magma ocean result in such a strong heating. I launch it again, you can see the correspondence here. It results in such an intense heating that we even have a reversal of the evolution of the magma ocean over this short period of time, where the magma ocean would reheat and rethicken. So here again, we led a parameter study in which we varied the reference viscosity of the cumulates. And don't read what's here, it doesn't correspond. But I will tell you what's important. So what's important is that when the reference viscosity is too high, we don't see onset of convection because the mantle is just too stiff to have convection, and we stick to the conductive case, which is this black dashed line. But as soon as the reference viscosity goes down a bit more, we see onset of convection, which always systematically translates into production of melt and heat piping that can be observed here on this diagram by the deviation of this colored line from the reference line. So the lower the reference viscosity, the sooner you start having heat piping, and the more intense it is. Still, we came up with this striking conclusion that regardless of the value of the reference viscosity, as long as you have onset of convection, it accumulates, you always have a convergence of the overall duration of the magma ocean lifetime between 180 and 200 million years. And we explained that by the fact that when the reference viscosity is still relatively high, it means that you will have a mild convection, which will produce only a limited amount of melt, and so limited effect of heat piping. And so only limited quantity of heat will be injected in the magma ocean. But this limited heating will occur below an already thick crust. So this little amount of heat will be hard to evacuate. While when you have very low value of the reference viscosity, you have really strong convection and really strong heat piping, but being injected in a magma ocean, which is overlain by only a thin crust. So whatever heat you put in is easily ridden. So in the end, you have this trade-off, which ends up to a convergence of the dose time series. So our conclusion was that this model, which we think is the most realistic so far, because it is largely, well, it encompasses a lot of effects, yields these robust results that the magma ocean, the lunar magma ocean, must have crystallized in 180 to 200 million years. So this is the main result of our study. And now at this point, so I'll jump on to the conclusion of this study on the thermal evolution of the magma ocean. So here I just briefly sum up the fact that the flotation crust is very important, is even actually more important as we previously thought, but also that we recognize the importance of internal heating as well as heat piping, which had previously not been considered. And that all these lead to a crystallization of about 180 to 200 million years for the full crystallization of the magma ocean. And at this point, I'd like to then say a few words on the consequences that this long-lived magma ocean may have. If you remember, I mentioned age estimate of the CRIP samples, which we think are representative of the end of the lunar magma ocean. So the idea would be simple. Then you would think, if you were to try to estimate the age of the moon forming events, you would say, okay, estimates for CRIP is 4.36 billion years old. Magma ocean takes 0.2 billion years to crystallize, so the moon is 4.56 million years old. As it turned out, that was not so simple, and this whole study on the thermal evolution is only one side of our work, which consisted after that in also reinterpreting the isotope age dating of CRIP samples in the light of this long-lived magma ocean. And what we came up with was a revision of the age of CRIP, which turned out to be significantly younger than this previous estimate. And that's because in this previous estimate, the age was derived under the assumption that the magma ocean crystallized almost instantaneously, which was consistent with the estimates from the Elkin-Stanton group of 35 million years or less. But for such long-lived magma ocean, it no longer holds. So we came up with this new estimate for the CRIP age, and in the end, we were also able to constrain the formation of the moon forming impact between 4.40 and 4.40 billion years ago. And yes, as I said in this talk, I only presented the thermal evolution model, but of course, if you're interested in the whole isotopic study, I refer you to. It's not written here. Okay, I refer you to the article we published earlier this year. And with that, I will finish this talk, and I'm glad to answer your question. Thank you very much.
Thank you, Maxime. Very detailed talk and very new results. How long have you been working on this problem?
That's I think we started that in 2017, late 2017. But yeah, we really started working on having this consistent thermal evolution model in 2018, I would say, early 2018.
This kind of 3D convective simulation is very powerful, you know. So
yes, and what's interesting actually is that our goal was not at all to develop this self-consistent thermal evolution model and to estimate. We were more focusing on trying to understand the titanium content in the Mare basalt, as I mentioned at the beginning of the talk. But I mean, it just came across that we realized that we needed to this consistent model, and then we just went all the way to studying the thermal evolution of the magma ocean, which was quite rewarding because we came up with significant results.
Okay, very good, very good. Any questions to Maxime, to Dr. Maurice? Any people listening, you know, working on the same thing that could ask him questions? I think he's very advanced in this field. It's a good time to know to ask him questions. So the main result is that what I have learned is that the crystallization time is at least about 180 to 200 million years, right?
Sorry?
I mean, the main result in your calculations that is the time taken to crystallize the lunar magma ocean. Yes,
exactly. So as one can see in this time representation of the constraints that we have, we had indication that the crust might have formed over about 200 million years, and it seems to be contradictory with the previous models. So in a sense, we can think our results to comply with this constraint, but in the same time, all these crust isotope dating are to take with a grain of salt, because, as I said, they might represent later modification of the isotopic states of the samples, and also well, it's just better to have, the more samples you have, the better the data can be, because it's highly possible that one sample is just not representative of the geological processes. So here I would like to back what Jim earlier said, and say that having samples is just makes such a tremendous difference when it comes to these kind of studies. And it's sometimes so frustrating that, I mean, we have more than 200 kilograms, I think, of lunar material, but still there's so little that we can say, and it feels like there would be so much more to say if we had just larger access to lunar material, which I hope we will have in the near future, thanks to landed missions.
So how many? You want 2,000 kilograms?
thing. I don't remember that. That's just like the. I think. Well, we would have to sum up to add up all the what the different Apollo and Lunar missions brought back. But I think that's something about 100 or 200 kilograms.
So in your model, you assume the moon is uniform, right? I mean, spherical symmetric model.
Well, not for the convective models.
Because correct. But I was thinking in terms of, about the near side, far side, the crust thickness difference. And
yes. Well, I know people have been investigating at the asymmetrical crystallization of the lunar crust. I think Mathieu Lanneville in Tokyo, in LC, worked on the topic. And there have also been other processes which might involve post-magmotion crystallization processes. Actually, if you have a degree-1 convection pattern in the mantle, then it would most likely result in this degree-1 anomaly that we observe in the dichotomy, in the far side near side dichotomy. And indeed, the degree-1 convection pattern has a long story of has been claimed for a long time to explain this asymmetry.
The recent study says that the moon might not be, at least the interior might not be as dry as we thought before. Would that have any effect on your work, on your modeling?
Well, yeah, indeed, how the water content in the moon would play a crucial role when it comes to being more quantitative on the reference viscosity of the convecting model, because the more water you have, the lower the viscosity gets. So it turned out that, as I've shown, that regardless of the viscosity, as long as you had onset of convection, you would expect more or less the same lifetime for the magmotion, but still what's happening in terms of mixing of the mantle could be very different, because if you have a wet mantle, which means a low viscosity, then you would probably achieve a much greater degree of mixing. And here that would be essential when it comes to mixing the high titanium reservoir into the bulk of the lunar mantle, and that could help explain the titanium content of the mirror basalts.
Okay, thank you. Any questions from the audience? If you have questions, please unmute yourself and ask Dr. Maurice the question. If not, no. If you have thought about any questions, I think Dr. Maurice will be happy to get your questions and answer.
Definitely.
And then if you don't have the email, and then send it to me, I pass it to him. So if no more questions, I would. It's almost noon now. So thank you, Maxime, and have a nice day in Texas and very successful work in 2021.
Thank you very much, and thank you again for inviting me. And unfortunately, I won't be able to attend the latest seminar today because, well, it's gonna be time for me to go to sleep. But have a nice end of seminar.
In a few months, we will ask you back to give another talk. All right, good. Then send us a new picture, with hair and beard.
Yeah, right. I will do.
Okay, thank you. Yeah. Bye-bye.